This was an amazing talk by Zhaozhan, and Zhaozhan beautifully introduced disk breaking, all those various non-axisymmetric effects that happen in planetary systems. It turns out a lot of similar physics is taking place in black holes, and even without a perturbing companion. So I'm going to talk about how black holes burp and shine. So let's see what I mean by that. And what I mean by that, I will focus on two different aspects, the accretion disk and the outflows and the physics of the interaction. So namely, kind of the line through my talk will be, I will be a black hole diatologist, actually a jet diatologist. I will try and figure out what do we give the black hole to eat in order for it to burp out stuff. If black holes burp out stuff, that's good for us, right? Because we can see it on the sky, transients, more grant money, more new missions. This is good, right? So get excited, wake up. This is going to be fun. So what sets the amount of burp, the jet power? Important question. How does it relate to the amount of the stuff that the black hole ate and what it ate? How do these outflows and burping get produced? And how accurate are our simulations? So let's say I ran a simulation, somebody else ran a simulation. Do they always agree? That's an important question, especially when the results that we make are going to be used for planning future missions. Another really interesting question is if the systems are misaligned, like Zhaozhan, for instance, studied, we expect the same misalignment in our case, in case of black holes, because the gas that comes from large distances has no idea which way the puny little black hole's rotational axis is pointing. So in general, the angular momentum axis of the infalling gas will be misaligned by pretty good, maybe 1 radian or so angle relative to the black hole rotational axis. So what will happen in that case? Will the black holes burp the same way? And if they do, which way will the jet go? Will it go along the disk rotational axis or the black hole rotational axis? Maybe none of them. It just won't happen. An important issue is if a black hole is luminous. And that's very important because we can see them far away. Black holes grow the fastest, can affect the galaxies. How does radiation affect the physics of everything that I just discussed? And finally, well, kind of end on a upbeat note, well, when the jets slam into things, eventually they will disperse and give the energy to the surroundings. So it's really important to understand how they die in that process, how they give the energy to the ambient medium. Okay, so let's buckle up and let's get going. I'm kind of going to define the landscape of black hole diet. The vertical axis here in this 2D space, it will become 3D in a second, is the thickness of the disk. So at the top, the disks are puffy and hot and don't radiate much. That's why they're puffy. They didn't lose the energy due to radiation. And at the bottom here, the disks are thin. That's because they've given their energy to the photons that then stole the heat. So they've collapsed and become thin. On the horizontal axis, I'm going to look at the amount of vertical magnetic flux. In the previous slide, you saw that there was a really nice, powerful jet, and these were magnetic field lines that were brought by the disk to the black hole. The black hole rotation wound them up into the springs, and the springs expanded and pushed the gas out of the way. That's how the jets form. So when we have a lot of vertical field that black hole can eat and wind up, that's good. So that's why on the top right here, I put a checkbox. I'm not going to even bother showing you results. This is when the jets, we know they are produced. Much more interesting is what happens when the disks are either without the vertical flux. Let's say it's azimuthal. We don't know. Maybe that's when the jets won't be there. Or maybe when the disks are thin, because the magnetic field can just rip through the disks and run away. And this is particularly interesting case when everything is going against the jets. And you will ask me, Sasha, jets are so exciting. Why are you trying to kill the jets? Well, that's because 90% of quasars don't have no jets. Right? So, I mean, we have to figure out when they don't form. Okay, so let's try this one. All right, so this is a torus on an orbit around the black hole, right? Yellowish is high density. It's a log scale. Blue is low density, so it's really a donut with a hole. Just so it's a fat donut It's a geometrically thick disk. Remember, it was on the top left. And you see that, you will see in a second that soon there will be vertical magnetic field appearing that you will see with magnetic field lines. But so far, right now, the field is coming out of the board here, coming into the board over there. And this part is zooming on the central region here. This is 100 times 100 gravitational on the side, vertical slice through the black hole rotational axis. And this is 1,000 times 1,000. So you see two different zoom in levels. The spin is nearly maximum, 0.99 of the maximum spin. No vertical magnetic field, as I said. And the disk is pretty thick. H/R is actually 0.3, but it's a log, so it looks like thicker than that. All right, let's get going. So I didn't want to get a jet, so I started with toroidal field. I went on vacation, I came back, I saw this. It's not supposed to be a jet. This has never been seen. What we're seeing is a dynamo akin to that in the sun that takes toroidal field and produces poloidal field, and then maybe it will flip the sign, every 11 years. So indications are that this is alpha omega dynamo in action that produces large-scale dipolar-like magnetic fields. You see huge magnetic field loops on a global scale that keep growing, keep getting bigger. This is the first time we see anything like this. This is really exciting. This is really good news for black hole burps, because even if you give black hole the wrong geometry of magnetic field, it can turn it around and produce something that looks like a jet, has vertical magnetic field. This is super, super cool. Why haven't we and other groups seen it before? It's a little bit of a mystery. One possibility is that we went to an insane resolution, because you need to resolve the MRI wavelength of the newly freshly generated vertical field, and that's why we had to have quite a few cells. And you will say, wait, Sasha, that's high, but what if you went twice as high or 4 times as high? Would it all change? That's a good question. Hold that thought. Before I do that, before I go there, I wanted to say that these two great students have been working on understanding the alpha omega dynamo, and that's why we think that this is alpha omega dynamo, I think, here. And also what I wanted to say is that even though we started with purely toroidal field, we got a lot of vertical field, we've got more than we signed up for. If we plot the dimensionless jet power as a function of time here, ignore this mass accretion rate magnetic flux, we focus on this one, you see that it asymptotes to about 150%. It means that we're getting jet power that actually exceeds accretion power. And this is a telltale sign of dynamically important magnetic fields developing. So we start with something that couldn't accumulate. The toroidal field can just be eaten by the black hole. And we ended up with something that accumulates to the point when it starts to dominate the whole dynamics, or enters the magnetically arrested disk or a mad state, which is awesome. It means no matter what we throw at the black hole, it seems the jets are there, which brings me back to the old question: how do we get rid of them? Okay, so how do we get rid of them? We're having fun with magnetic fields, general relativity, and we try to run it on graphics cards. Graphics card, I really like the analogy. Graphics cards, okay, CPU is like a Ferrari. Let's say you want to move to Santa Barbara. I definitely want to move to Santa Barbara right now. Okay, so let's say in my cold city of Chicago, I try to put as much stuff as I can on the CPU, on a Ferrari. And maybe I will attach a door handle, maybe it will fit one leg of the chair. That's it. It won't fit anything. It's really fast. I can make a lot of trips. It's really powerful and smart and cost a lot of money, but it doesn't mean I can do as much stuff with it as I naively thought I could. On the other hand, let's say Ferrari has 400 horsepower engine. I could get 400 horses, and as long as I give them enough grass to eat, I can, on one horse I will attach one chair, on the other another one. Maybe I will attach a washing machine on the third one. They will be slowly moving their way to California, but eventually they will get there and they will beat the Ferrari. I'm pretty sure of that. So that's the GPUs. That's the power of GPUs. If you can break up your complicated problem into little chunks and feed each horse individually, or a thread of a GPU individually, you're going to be golden. And that's precisely what Matthew and Koshik have done. That's how we converted our code that's called HAMR onto GPUs. It now has radiation with a 2-moment OM1 closure, shows excellent scaling to thousands of GPUs. And what's really important is that it has adaptive measures not only in space, but also in time. So we refine not only in space, but also in time, which is technical, but that gives us an extra factor of 10 speed up on top of the about a factor of 100 speed up of one GPU versus one CPU core. Okay, so CPUs have maybe, let's say, tens of cores. So we get roughly factor of 10 speed up, one CPU versus one GPU. Sorry, one GPU versus one CPU, plus extra. Why do we need all of this? Well, you will see in a second. We can get a lot of computational time on national resources, and we can ask really hard questions. So let's see what the answers bring. For instance, I asked you, what if we were to double or quadruple the resolution? You thought I was joking? No, we've quadrupled the resolution. When you double the resolution in every direction, the cost of the simulation goes up by a factor not 8, but 16. When you quadruple it, it goes up 16 squared. So this simulation is ridiculously expensive, okay? And you would say, why do we want to go there? Clearly, there's no new physics that will appear. Well, let's try and see. So this is, first of all, you can see the details shown in plasma beta on the right, the insane, clear structure of the disk with lots of current sheets, which is fascinating. But if we were to zoom in, and even more, I mean, and there is more resolution over here. I mean, it's limited by the snapshot from the figure. I just blew it up. You can see that there is structure in the sort of current sheet that separates the two jets. And that's real. That's actually plasmoid instability for the first time seen here in 3D around the black hole. And that's a big deal, because once you get into a plasmoid dominated reconnection regime, the reconnection rate no longer cares about the resolution. It only cares about the fact that it's there, and then it settles on a well-defined reconnection rate. So we are finally getting into the regime where we actually can say, aha, reconnection rate is independent of our resolution, which is a big deal. It means that we now have the hope of actually being more confident in our simulation results. All right, so good job us. Here, jets, there, jets, actually not us, the black holes. We didn't do anything, we just figured out what they knew already. Okay, let's now tilt the whole system at the third axis. And let's try to break the jets this way. So what will happen if we tilted the system? Will the jets be there? Well, so this is a disk shown in blue, tilted by 45 degrees. And the jets, you can see, spoiler alert, are still there, and they're tilted. And because the black hole rotational axis is vertical and the disk rotational axis is tilted, the black hole drags the space-time around that axis. So it pulls the disk around with it because the disk is embedded in space-time. So that's what causes the disk to precess. And this disk takes these jets with it, and they also precess, which is a big deal because this spreads the jet power over a large solid angle. So it does more feedback if you embed the system, let's say, in a galaxy. Or if you have a mini disk that's precessing, you will have a lot of interesting effects that will be generically three-dimensional. So that's really cool. Oh, and if you see this precessing jet in a radio, and you can then infer something about purely general relativistic effect of precession. Awesome. Okay, so if you tilt the disk by 90 degrees, the jets still survive. We still can't get rid of them, even that way. So even these ridiculous cases, when you have misaligned spins and mini disks, maybe you've seen something like this there. I would love to talk to you who work on the binary black hole problem to try and understand if something like this can affect the torques and the outcome of the system. Okay, we haven't been doing so well so far. In all of these cases, the jets are there. Let's try and go to our, last resort and try and look at a thin disk. It's easier for the magnetic fields to escape from a thin disk. So maybe that's when the jets will not be there. Also, if the disk is thin, maybe it won't be able to collimate the jets, so it will fall apart. So there are many reasons to be happy about this system if you don't want to see the jets again. And I've seen a lot of them, so believe me. Maybe sometimes I don't. All right, so this is a black hole with a spin that's vertical. It's 93% of the maximum, so it's pretty fast spinning, tilted by 65 degrees. And now we're considering a disk of much smaller thickness, like we promised. We start with 0.3, now it's 10 times thinner. All right, so what is this? I think that there is a jet. And there's something else that's really weird. So in 3D, this looks like that. So the disk is torn. And let's take a look at the movie, how it works. Okay, so this is a disk tilted by 65 degrees. That is a jet going out. The black hole's rotational axis is vertical. So that's why there is a tilt. Let's press play and see what happens. So the black hole spin causes the inner disk to precess, but it's too lazy to carry the outer disk on its back and cause it to precess its work. So it can't do that, or it refuses to do so, it tears. And then the jets, they smash into the original disk and say, dude, you were too lazy, and destroy it. Okay, that's pretty gory, sorry. And then the disk continues tearing up into smaller and smaller subdisks. Eventually, you have the original, this one, that one, 4 disks. And the inner one actually gets aligned, which is a big deal. I'll get back to it. Sometimes disks merge, and then they separate. You can see this one just precessed through the line of sight, probably occulting the central regions. There is a lot of potential for variety of transients over here. So when you're seeing something that is changing weirdly on the sky, maybe that's a disk that's precessing. It doesn't look like a regular disk. See, they merge together. You can see the central region, and then they will separate out, and you will see through that. Of course, this is just a rendering. In reality, we need to do proper radiation transport, which we have done, and I will show you in a second. So this is really cool. Lots of extra dissipation, extra observational consequences where I didn't expect anything that exciting. All right, so far, no luck, no dice. Jets are still there, can't get rid of them. Okay, since I'm on the mission to destroy the jets, let's go here. Let's take everything the jets need. Disk thickness, gone. Vertical field, gone. All right, so this is a 3D rendering of a disk that's tilted by 70 degrees relative to the black hole rotational axis, which is vertical here. And this is a vertical slice through the meat. As usual, red is high, blue is low, 10 orders of magnitude in between, so blue is vacuum essentially, and red is the meat. Okay, so the thickness of the disk is even smaller here, but what's important, why am I showing you this? How is it different than before? It's because this disk doesn't have any vertical field, so there is nothing that's sticking out of it. All the field is purely azimuthal, it's inside the disk, it's packed inside the disk, so hopefully that will prevent the jets from forming. And we will see, are all those effects that we saw previously because of the jets? Or maybe they don't care and the disks behave the same way, even without the jets. So you see that the dragging of the spacetime causes the disk to warp. It's like a membrane that was pulled in the phi direction. And this pull sometimes is too much for the disk. So the inner parts of the disk get torn off from the outer disk and get consumed. And you can see this both on the left and the right panel. And this happens quasi-periodically. It happens all the time. You will see that there will be another a little bit bigger event that's brewing over here. Whoop. And there will be another one, you see it here, that is going to be more long-lasting. See, it's precessing. So probably there will be some sort of periodic modulation that we will see from the surface of the disk, changing its angle, which is quite exciting, perhaps. Periodic signals, nice. The inner disk aligns with the black hole, big deal. Since 1974, I think, we've been looking for Barton-Peterson alignment. They predicted it, but we've never seen it in the turbulent disk around supermassive, around the black hole in general relativity. This disk eventually gets consumed. So that's really awesome. We are finding that both disk tearing and that alignment that I pointed out in the original movie, they are generic. They don't care about the geometry of the magnetic field. They seem to be happening if the disk is thin enough. And you can see how thin it is over here. We can make an image of this disk and ask what are the light curves. I'm not showing the light curve. I took it out. This movie is done by Andrew West in Washington University at St. Louis. But what's really cool, you can take this light curve, take a Fourier transform, and look at this periodogram. And what you see is that there are 3 peaks. For 10 solar mass black hole, 115, about 90, and about 60 hertz, which comes in ratios of 2, 3 to 2, and 1. So we have both 2 to 1 and 3 to 2 ratios of these peaks, which are this sort of, not perfect oscillations, but quasi-periodic oscillations, which maybe is what produces them in black holes. This 3-2 is particularly exciting because it was extremely difficult to figure out what causes that. 2-1 is a harmonic, 3-2 is much harder. We still don't know what is the physics behind that. This is really in preparation. I should have put in prep. Andrew has just made this movie literally and gave it to me this morning. Okay, so you said, Sasha, but was there radiation in this disk? How was it so cool? Well, okay, it's cool, thank you. But it is cool because we prescribe the cooling function. That's a standard approach in general relativistic business, where we just say, okay, well, I would like to have a certain temperature profile given by Shakur and Sunyaev and Novikov and Thorne, those people who were at the origin of the sort of thin disk theory. What about radiation? Well, here you go. I'm glad you asked. This is the same exact simulation that we stopped. And, once the disk reached steady state, so it has gone on for about 30,000 dynamical light crossing times of the black hole. And then we switched on the radiation within a 2-moment approximation for the experts. Don't worry about it. Just radiation can push the gas around. So this is the same view as before in 3D. This is, we flatten out the disk. Like if you have a pizza that's warped, you flatten it out. And you see that, just to give you a sense for the non-axisymmetric modes. This is the electron temperature. This is what is going to radiate. And this is the emissivity. So let's play the movie and see what happens. So one thing you notice immediately, that temperature is non-axisymmetric. So we cannot just represent a warped tilted disk as a bunch of axisymmetric rings. For radiation, it doesn't fly. So that was completely unexpected for us. When the disk tears, you see that there are features in temperature, and even the emissivity of the whole disk flares up. That's the end of the simulation. Unfortunately, radiation is more expensive, so we can't run it as far. But this is really exciting. This, for the first time, perhaps can tell us what the radiative signatures are of disk tearing and warps. Okay, now, maybe you've heard that disks are truncated. This is work by Ising in 1997. A lot of us have seen this. At low accretion rates, this is the Eddington ratio. The disk goes up, goes down, thin disk goes down to like a largish radius, maybe hundreds of gravitational radii, and then it kind of transitions to this corona, like this kind of fluffy, dilute bunch of black points. And as you increase the Eddington ratio, then the corona shrinks and the disk collapses on the black hole, meaning its inner radius goes closer and closer. It has been a huge challenge to try and figure out what says the physics of where the disk truncates. This is another view. This is called the Q diagram, where this is the hardness of the system. So hard spectrum is on the right, soft spectrum is on the left. So this will be hard state. This will be a soft state. And top is bright, bottom is dim. So if we, let's say, start with a system that was dim, it was hard. And so the disk was yellow, and yellow means fat and fluffy. If we let it go up in brightness, it launches a jet, becomes brighter, but it is still hard. So it's a thick disk. Now, if we wait for longer, it travels to the left, becomes softer. And here you see there is a thermal disk, which is shown with the red, with a little bit of yellow. So there is a combination of the two. Weird, right? And then eventually it comes here and settles down on the thin disk, and it looks like a razor thin disk, and it's all red. It's all soft thermal emission. So you can quantify this. Of course, this is a cartoon inspired by observations synthesized by Fender et al. In 2004. So you can see that the disk, inner disk radius, the radius of that red thing, is large at low luminosities, and on the right of this figure, and it shrinks as the system transitions to the left. This is called the spectral state transition. And then also the jets are launched over here, which is not the focus currently, but it's nice to have the jets as well. So what is the physics that makes this transition to be so sharp? There are lots of ideas. I will show you one that seems to do a pretty decent job. Let me know what you think about that. In particular, what I will focus about is the sort of heart of the state, like this kind of luminous hard state in the middle. where there is both the red and the yellow. It's a two-phase medium, cold and hot at the same time. You see both a black body, which is cold, red, and you see power law, which is yellow, all at the same time. So you have to have cold stuff illuminating the hot stuff that upscatters and makes a power law. So this is what may be happening, and this, I already showed this slide a couple of days ago. It turns out that in order to truncate the disk, one way is to put a magnetic put magnetic fields in the way so that there will be bottling effect where magnetic flux accumulates and heats up the gas, and it actually naturally develops a two-phase medium. So the right is a zoom in on the left. This is a simulation with a lot of vertical magnetic field. This is slice of density. This is without vertical field, purely with toroidal field. And you see that here the disk actually does break up into cold, dense clumps embedded into something that's much less dense. In the case of no vertical field, that doesn't happen. And you can see that this clump is low temperature. This is ion temperature. And low electron temperature. So these are actually cold clumps. They will radiate thermal emission at a low temperature. And it's all embedded into this hot ion fluff, which is probably the corona, the lamppost that emits hot emission. The electrons here are at lower temperature than the ions because it's low density. So Coulomb collisions are not efficient at bringing the temperatures together, but they're still hotter than the cold phase. It turns out that, in the range here, so you see kind of yellowish, it's like somewhere between 10 to the 8 and 10 to the 9 Kelvin, which seems like it's in the right ballpark. So this is really exciting. If this is indeed what's going on in the sort of transitional state, maybe we're coming closer to understanding what governs the way the black hole eats up stuff. There are also interesting things here. If you zoom in on the structure of this disk, there seem to be plasmoids here as well. So there could be some interesting radiation signatures from that. Now, let me go really quickly with a few highlights that perhaps some of you are interested in. You can ask me questions later. What is this galaxy? This is weird, right? There is one set of jets which is new. It looks like there's another set of jets that are old. Could it be a binary black hole, each producing its own jet in different directions? Could there have been a spin flip in direction due to a merger recently? That would be exciting. Or could it be maybe these jets created backflows that kind of non-axisymmetrically went away? Would be nice to know. What I will say is that you can make all of this with 3D instabilities, starting with purely axisymmetric conditions. So these are axisymmetric conditions. We have a Bondi radius, which we reduced down to 1,000 gravitational radius of the black hole. So uniform density outside, hole inside. We add rotation, comes out, goes away. And we have vertical magnetic field. These are the only three ingredients. Oh, yes, and the black hole spin is vertical here. So let's run the simulation. This is work done by Aris Halakos, graduate student. Look out for him. He will be on the job market, not this, actually this fall, yeah. So you see what happens. It shoots out. Let me restart the movie. Maybe. Oh, I can't restart the movie. Yes. So this hole collapses. There is a shock that emerges. And somehow the jets go sideways. These are the jets. And then there is a new set of jets that goes up. So if we were to pause this, which I won't, you see that there is an X-shaped structure that emerges naturally. So due to 3D instabilities, when the jets are too weak to go up, they're slammed by the gas and they go sideways. That can naturally lead to the sort of wings that look like an X shape. You can have more of the same in collapsing stars with rotation. Now, rotational axis is horizontal here. This work done by Or Gottlieb, a postdoc at Sierra Northwestern. And you can see that the zoom in shows that the jets do launch. And the fun part happens when the jets try to push through the ambient medium. And you can see that this one goes to the side, this one seems to be okay, but then there's a new element of the jet that's going at a different direction. So it's possible that when stars explode, they don't produce one GRB or two GRBs because the aliens will also see it. There could be multiple GRBs because the jets have multiple components that will have pushed out of the star at different angles. And this is, as far as I know, the first GR MHD simulation in 3D that shows how the jets go from the black hole all the way to the surface and outside, which is opening the possibility of connecting the central engines to the observables. You don't have to collapse things, or you can just send black hole through a uniform medium. which has interesting applications to wind-fed systems, as I learned at this conference. And so this is what Nikas did. He sent a uniform gas at map number of 2.5 on a black hole over here. And all he did, he added vertical field. And what's interesting is that the shape of the shock and everything is changed dramatically due to the presence of jets. And not only that, the presence of magnetic field seems to lead to negative drag, similar to what we heard earlier in the presence of outflows. Here, it's all formed self-consistently. I am done with my time here and with the talk. So here's the summary. No matter what you do, almost, jets are always there. It's really hard to get rid of them. You have to do everything in our power to get rid of them. In the presence of large-scale magnetic fields, you have to take away the vertical field, and you have to make the disk thin. That's the only way to get rid of them. If you immerse your jetted system in ambient medium, it will explode the ambient medium, and the jets can fall apart and impart the energy to the ambient medium, which is really exciting. If the black hole and the supply of the gas are misaligned in terms of their angular momentum direction, you can have really interesting effects, such as the alignment of the inner part of the disk, the breaking of the disk off of the outer disk, and the tearing of one disk into multiple independently processing subdisks. That can lead to quasi-periodic oscillations. A lot of exciting phenomenology that we couldn't understand and interpret now might be coming to light. If we go to insane 3D resolutions, we can find new physics, like plasmoid-mediated reconnection, which is really important in establishing the ability of us to get converged results. And finally, including the radiation can reveal this really exciting truncated disk states self-consistently and allow us to interpret the observations better. Thank you so much, and sorry for running over.
Thank you, Sasha. We have a lot of questions. We go from Ben.
It's a really nice talk. So of course I'm thinking about mini disks and circumbinary disks. And in that case, the black holes in a binary, right? Their disks are fed from a specific initial condition from the streamer's pulse stream accretion from the circumbinary disk. So calling on, right, the circumbinary GR-MHD simulators in the room and what you've talked about here and how to make jet. What do we expect for the jets being launched by these mini disks, knowing what kind of magnetic field is being fed to them from these streamers? Can we start to say something based on these simulations on what the jets would look like for these mini disks?
So if these mini disks are super Eddington, as far as I learned at this meeting, right? Like quite a bit super Eddington, because you worried the black holes will grow out of control. So that's got to be like 10 Eddington or roughly.
The Eddington right onto the mini disks?
Yeah.
I guess, yeah, we're not.
Well, it could be anything, depending on
Eddington,
yeah.
not 10. Okay, so
yeah.
if it could be Eddington, then we're probably dealing with something like this. So this is good. I'm really glad that
I think in our PG 1302 model, it's like up to a few Eddington onto the secondary.
So if this is a few Eddington, this is 30% of Eddington. You could have something like that in that system. If it were vastly super Eddington, then you would have had a thick accretion flow. It would be even easier for it to produce the jets. If you are around Eddington, you can have something of this kind. You could have perhaps disk truncation if you have vertical magnetic field. Otherwise, if you don't have vertical magnetic field, you will have a jetless state like this. And it seems like it undergoes a runaway cooling. So it is radiatively unstable. And it would be really good to try and understand observationally what the consequences of this are.
Yeah, and what the magnetic field structure in the stream feeding the disk is.
That would be nice, yeah. It would be really good to go talk to people who can simulate that.
Thanks.
Thank you.
We can go to the junior ones, but wait a second.
Sorry, I didn't know you were coming for me. Otherwise, I would have closed the gap. I'll talk a little bit in my talk this afternoon, and so maybe I'll raise the question I have regarding the magnetic field evolution in the binary system then. But what So one of the things I find really intriguing is the case where you're starting to resolve the magnetic islands. So with a magnetic truncation radius in a MAD system, if it's not too far out, then the dripping cool material won't have time to absorb, I would think, or at least what I see, doesn't have a lot of time to absorb the magnetic field. So I would expect the magnetic Prandtl number to be extremely low still. So what is the magnetic Prandtl number in the dense filaments? And do you resolve the turbulence in those filaments like you would have to really be hitting that resolution stage?
So this is a really excellent question. So these islands, they are supported by magnetic pressure. And we also took a precaution. We don't allow them to cool down to the grid scale if they wanted to. We tested two different kind of runaway prevention mechanisms, and we found that the results didn't care. So it seems like once the islands form, they are highly magnetized, and the magnetic field is really bolted to them. It can't escape.
Right. But so in a real disk, wouldn't you expect the dense material between the islands to still be gas pressure dominated and still have some turbulence, given the low Prandtl number?
Well, the gas around the islands is highly magnetized as well, because the magnetic field strength is the same, but the density is much lower.
Okay.
So it's all really highly magnetized. I would love to talk about this more. This is a really new and interesting system.
Yeah, that's really exciting, Sasha. My question goes back to your idea.
Who's talking?
This is Bhupendra Mishra.
Oh yeah, but can you raise your hand so I see where you are? Oh yeah, here you go. Okay.
Yeah, great talk. So I believe these are for low mass black hole X-ray binaries.
This was simulated for LMXBs, exactly.
Right. So do you think it will be great that you can go back to slightly lower resolution, run it longer to see if you can get the state transition? How long these truncated disks last in your models?
That's a really good. So this simulation shows here it's 200,000 RG/C, which for those who are in the room, that's pretty long, especially for these insanely thin disks of H-AMR 0.02. I think that this is the thinnest disk simulated ever in GRMHD, and we've pushed it all this far. So this is really state of the art. We probably can push it longer, but we're afraid we need to push it. You know, the state transition takes like a week. Let's say even a day in an X-ray binary. A day is 10 to the 5 seconds. A light crossing time of the black hole is like tens of microseconds, sorry. So there is like 10 order of magnitude scale separation that we can never be able to bridge. So maybe we will start seeing first indications of magnetic flux leaking out. That's what we want, right? We want the jet to shut off. This magnetic flux that's sitting here to leak out. We haven't seen an indication of that. We've run a non-radiative simulation of this. That's in fact what was the initial condition for this radiative simulation. And we haven't found any indication that the magnetic flux is leaking out. So something is missing, or we don't run in long enough, or perhaps we need to include non-ideal physics with actual physical Prandtl number, and maybe it's not close to unity. I'm really open for suggestions. Right now, we're stuck. We don't know how the magnetic flux leaks out and the state transition happens.
Sasha, great talk. Am I on?
Homer, yes, you are.
Good. When you were showing us the alpha omega dynamo thing with a thick disk initialized with a toroidal field,
Yes,
you posed the question of whether this is maintained if you get a higher resolution.
correct.
And then you talked about the admittedly interesting things about the, you know, the plasmoids and everything.
Yes.
But you didn't answer that question. So
No.
do you still see toroidal flux being converted into colloidal flux and generating a jet? Or have you done that at high resolution and run it for long enough?
I guess I admit that this is where the story was a good one to tell in order to motivate what was happening, but I actually didn't have anything to show for it. We haven't run anything at higher resolution than that. In my experience, so if we go to slightly lower resolution, we still see the same effect. So it's not just at this resolution. It turns out that after the fact, we've run simulations at half of that, and it still worked. So that's a good sign, but we haven't increased the resolution here. Yeah, I mean, unfortunately, once you've discovered something, the computational, resources They're like, you already discovered this. What's new is going to come here? Well, we'll study convergence. Like, not interesting. So it's been a bit tough for us to repeat this at a high resolution. But if there is a good science case that we can make, I would love to talk to you about this. I would be all for that. Thank you, Omar.
Hi, Sasha. Great talk. Adam Dempsey here. In your 2T simulations, maybe you checked this in post-processing, but is the conditions in the electron fluid, like the gradients in the electron temperature and density, the right conditions to generate a strong magnetic field from the Biermann battery? This might be
I
a way
see.
to generate a colloidal field from nothing.
Yeah. There have been works on that, and there were findings that if you artificially increase the Biermann battery term by, like, I forget how huge factor, maybe 1 million or something, or even more, then on a very short time scale in the simulation, you can generate large scale magnetic fields. We haven't tried to include that. My suspicion is that everything will fall in way before the Biermann battery will have a chance to do anything, except maybe for really, really thin disks. But we haven't tried that. It would be good to make a back of an envelope estimate of this. Thank you, Adam.
So Daryl Haggard, all the way in the back. Thank you, Sasha, for the very nice talk. I'm wondering whether or not this tearing, which was such a kind of persistent feature and happened over and over again in some of these models, is this something that happens only in specific circumstances, or do you think that this re-tearing and gobbling of the inner disk is something that's ubiquitous in all of these, in all accreting H-AMR? It seems so sort of...
It seems to be very generic, I agree. As long as the disk is thin enough, and at least in our studies, this thickness is 1/30, so 0.03. That was the first thickness at which the tearing happened. At 0.5, it didn't happen. At 0.3, it did. So if the disk is luminous enough, like maybe in the range of 1% of Eddington to, I would say, 50% of Eddington, and the system is tilted enough, because this tearing we found only happens when disk is tilted by 45 degrees or more. So high tilt, thin disk, it seems like there's no way to avoid it. So it has to be there. Thank you.
On the way to calling on somebody else, I'm going to sneak in as a coordinator and ask a question anyway. So this is related to this. I mean, so Xiaohuan showed, very nicely how you can basically predict when tearing happens analytically. Have you tried to apply any of these criteria? Maybe you need to, worry about alpha and wave communication as well.
There is a graduate student who is working on this. There is a lot of disk tearing theory that has been developed that I completely didn't mention. There's a huge body of work. We just came in and said, let's simulate that. But there is a lot of analytics that predict when the disk tearing will happen. And it seems that when we plug things into our simulations to check whether the criterions for tearing that they developed work, by order of magnitude, they seem to be working, except there is a lot of variability. The same disk can tear here or there, depending on its liking. If you plot the precession angle, which shows a discontinuity when the tearing happens, you can see that there are multiple tears that try to happen at the same time in multiple places, and then one of them stochastically wins. So it's a little bit hard to say, yes, it works exactly, because there is generic stochasticity. That's why we didn't really try to push it too much so far, but it's a really good direction and line of questioning.
Well, let's take question from online. Andrew?
Yeah, so I guess in the spirit of building the bridges on the tearing here, so Xiaohuan argued that the tearing causes a very deep gap that cuts off communication and is hard to close, whereas you showed the opposite. Is there a way of understanding this difference?
So thank you, Andrew. I think this is precisely why these meetings are so exciting, because now Xiaohuan and I can see each other face to face after 2 years of not seeing a live soul, except like inside the house, and we can sort this out. The communication across the tearing definitely changes from between when there was no tearing to after when there was a tear. But let's say if we look at like the emission pattern, you will see that when the tear happens, the disk gets shaken up. So I think that there is indeed more to just completely losing contact between the inner and the outer disk. There is definitely some transport that's happening, and I don't fully understand that. So if there are experts in analytical theory of disk tearing, if those exist, I would definitely like to talk to you more. Thank you for the question.
Yeah, nice talk, Sasha. Yeah, beautiful simulations even break the projector sometimes. So regarding that, I think we are in a very different regime. You are in this viscous regime, very thin disks. This is highly turbulent. Alpha is very large. And in protoplanet disk, we are in this wave regime. I'm talking about alpha 10 to negative 4. So I think that is one big difference. You have very accretion throughout the whole disk with very large alpha.
There are some weights here as well. So it's not precisely viscous. So I think there could be more crosstalk between what we do than like a standard disk tearing theory in a thin disk can provide, because you can see the waves, like you can see the waves propagating. So it's not a, you know, just a viscous, structureless, featureless disk.
Yeah.
Thank you.
So I'll be brief. So how does black hole spin fit into this narrative of how do we kill the jets? Like, does that whole schematic, thin, thick, vertical, flux or not, assume that the black holes are always rapidly spinning? And like, I mean, how does that fit into the idea that, you know, we don't see these jets? Is that telling us something about black hole spin or no?
So, thank you. This is something that we're actually trying to figure out right now. Really great question, Laura. So this was run for a spin of 0.9. And the jets are there and it's exciting, but initially the jets were kind of sideways and kind of dying and things like that. So we actually realized that if we were to lower the spin, it's possible that we will never get the strong jet that gets out. Maybe it will always be stuck. So it could be one way of, like, let's say, reproducing radio-quiet galaxies, where you see some radio emission, but you don't see large-scale jet. So definitely, if you shut off the spin, the jets won't be there. But we know that that can't explain the whole story, because we know in X-ray binaries, in small black holes, microquasars, there are systems that cycle through different states, right? Like I showed in this Q diagram, where one day they don't have a jet and the other day they have a powerful jet, and the spin can change in those timescales. So I think what you are thinking of is a good way of shutting off jet formation at its root, but there has to be something else. Having said that, setting the spin to a lower value and trying to explore some of this physics could have really important manifestations. Like I said, radio-quiet galaxies perhaps indeed have low spins. So yeah, I would definitely love to talk to you in the context of global cosmological simulations and try and understand how our understanding of how black holes spin up or spin down due to accretion can fit in to population synthesis models.
So I'll take a last question from Julia and take photos.
Yeah. This question, in fact, is related to several of those that have already been asked, but I think it's worthwhile looking at this from a more basic point of view, which is that angular momentum transport across those gaps has to be taking place, because otherwise there wouldn't be continued accretion onto the system. Because there's strong MHD here, you know, unlike the protostellar case, conductivity is very good. So yeah, MHD approximation is excellent. There is a relatively high rate of level of stress, and that means that there is faster inflow. It means that the angular momentum delivered to material to align it, when it goes suddenly from this alignment to that alignment, is taken from the black hole spin. Angular momentum is conserved overall.
The misaligned angular momentum can cancel out. That's how Barton-Peterson effect was originally derived.
Well, to be precise, over time, the black hole spin of the black hole gradually aligns with the material that's being fed in.
Eventually, yes.
Yeah, and so it's worthwhile asking how much angular momentum is delivered at the location where that gap take occurs.
I see. So you're wondering what is the torque if the black hole realigning the disk, therefore the disk is realigning the black hole, how can we change the direction of black hole spin? let's talk about this, Julian, because this could be important for Laura if you would like to understand how black hole spin evolve. Yeah, it would be a really good.
And it's also a way of, if the material that's being fed in has a consistent sense of angular momentum and runs for a long time, that it eventually eliminates the tilt because they align with one another.
Yeah, over timescales when probably black hole mass had a chance to grow substantially. Although,
but there's a big multiplier,
and I
because the specific angular momentum out where the breaks are is much larger.
I remember we talked about this a while ago.
Let's continue the discussion.
Thank you, Julian. This is exciting.
Thank you.
Thanks a lot, everyone.